Today we'll talk about complex numbers for 8.5.5. So before we talk about what complex numbers are, we must first talk about what imaginary numbers are. Now, looking at the name imaginary, it is not too far from the truth. The idea of this number is actually imaginary, meaning that it doesn't physically exist in this real world. So an imaginary number is just any number that is negative with a square root on top of it. And the base unit of an imaginary number is I, which is the square root of -1. Now, you can see why it is imaginary, as we cannot have the square root of -1. Numbers underneath the square root, as you probably know, should always be positive. That is because the resulting value after the square root, if you square that number, it has to be a positive number. Because no two identical numbers, when multiplied together, will give us a negative result, at least in the real number world. So for example, the square root of 4 has two answers, 2, -2. But no matter what, when you square root either 2 or -2, you're going to get a positive 4. As in the case of a square root of -4, neither -2 or 2, when squared, can make a -4. So that is why we have the value of I to sort of act as a placeholder so that we can actually solve when there's a negative square root. Again, I is an imaginary value, so technically this does not exist in the real physical world, but it is still an important thing to discuss. Now, for example, if we have if we have x squared plus 1 equals 0, and then you try to solve for it, you're going to get something that looks like this near the end, where the square root of x squared equals to the square root of -1. But then using I as a replacement for the square root of -1, which is technically not possible, we can say that we solve for x, in which x equals to I. Now, I'm going to bring up a property that we talked about before. So the square root of AB equals to the square root of A times the square root of B. Why this is important is mainly because we're going to use this as a way to transform negative numbers in square roots so that it becomes a more digestible imaginary number. So before actually showing any examples, it's just that either A or B in this equation is going to be -1. And since the square root of -1 is I, we'll simply have a square root of a positive number with I multiplied to it. That is how we will transform most cases of negative square roots, negative numbers underneath square roots. That's what I mean. There's also another really important property of I. So that is its powers and how there is a consistent pattern in terms of what the value of I should be with a certain value as a power. So let's look at this trend. We know that I equals to square root of -1. I squared is -1 because, as you can see, -1 times -1 underneath the square root, all you have left is -1. Now, there are some very important patterns pertaining to I, mostly about how its powers share a consistent pattern in terms of what the number of I actually is. And let's understand this pattern by looking at this list of I and its powers with the results. So I by itself is just square root of -1. We established that. I squared, which is square root of -1 times square root of -1. You can see that the square root kind of cancels out to give -1. As with I to the power of 3, you kind of break it down into I to the power of 2 times I. And as we know, I to the power of 2 is negative 1. So this just gives us negative I. And as for I to the power of 4, we can break it down into I to the power of 2 and I to the power of 2, which are both negative 1. And as we know, negative 1 times negative 1 is simply 1. These four values are actually going to reoccur through any power or the whole number power of I. So if we look at the next four numbers after I to the power of 1, 2, 3, 4, now we're looking at 5, 6, 7, 8, we can see that they actually have the exact same results. And this is because we can kind of take advantage of the fact that there is at least I to the power of 4 in every I to the power of a very large number. And as I to the power of 4 is just 1, we can use this property to simplify and see what the actual value being represented by all these i's stacked on top of each other actually is. So basically the pattern is you should remove all groups of I to the power of 4s from a given power of I, and then see the number you have left. Or you can think about it like this. It's the power of I, you divide it by 4, and you just look at what remainder you have. The remaining value, or the remainder, is going to be what the actual value of I is in this question, or the I to the power of something. So let's use a very large power of I to see how this might work. So let's say we have I to the power of 63. Now, this might look really intimidating at first. 63 is a really large power, but since I are just reiterations of the square root of negative 1, we can simplify this into its actual value. So, as I've said before, a trick to finding out quickly what this I to the power of 63 actually is when simplified, simply divide by 4 and then find the remainder. So we have 63 divided by 4. As we can see, 4 goes into 6 one time, and then if we just simplify that, we can see that we have a remainder of 3. So 4 goes into 63 15 times with a remainder of 3. If I were to rewrite this in terms of just powers, what I'm doing here is basically stating this. I to the power of 63 equals to I to the power of 4 and then to the power of 15 times I to the power of 3. As we know, I to the power of 4 is just 1, so I to the power of 63 is actually just I to the power of 3. As we discussed before, I to the power of 3 is just negative I, because this breaks down to I squared times I, so you can simplify it as such. So my final answer would just be I to the power of 63 equals to negative I. So every real number has a counterpart imaginary number. This sentence means exactly what you think it means. So for example, if I have 63 766. It has a counterpart that is imaginary, that is just this. Now that we understand what an imaginary number is and some properties of it, let's talk about the title of this topic, a complex number.